Hello everyone, this is Professor Ng Chi Kun from Unimas. In this video, I'm going to show you an example of a two-way restraint solid slab design. So, we will be designing for this panel of the slab where it's continuous at two edges like this and this continuous at the other two adjacent edges. And then we are taking this direction as Lx and this direction as Ly. And then the Ly over Lx ratio is 1 for a square slab. So the characteristic permanent action excluding the self-weight of slab is 1.5 kN per square meter. And the characteristic variable action is 3.5 kN per square meter. Design the corner slab using grade C25 concrete and grade 500 reinforcement. Show the reinforcement on sketches. First of all, we specify the concrete grade and the steel grade. And then we mark down the characteristic actions. So permanent action GK is 1.5 kN per square meter. The variable action QK is 3.5 kN per square meter. And then from MSEN 1990 table 2.1 or Eurocode 2.1, the design life is 50 years. And then for durability, fire and bond requirements from Eurocode 2 Part 1-2 Section 5.7, the fire resistance is R60 or 1 hour. And then from table 4.1 of Eurocode 2, exposure class is XC1. And then from table E1N of Eurocode 2, for exposure class XC1, the indicative strength class is C20/25. So we're using C25/30 grade, so it's higher than the indicative strength class. So the structural class is S4. And then from table 4.3N of Eurocode 2, with member with slab geometry, we can reduce the class by 1, so it becomes structural class S3. And when we go through all the other categories, there is no increase or decrease in structural class. So the structural class remains as S3 after considering table 4.3N from Eurocode 2 after going through all the categories. And then from table 4.2 of Eurocode 2, we have separated bars. So for slab design, normally we have separated bars. And we assume our bar diameter is 10 mm. So our C min B is equals to the diameter of bar is equals to 10 mm. So C min durability from table 4.4N for exposure class of XC1. And then we have C min for durability equals to 10 mm as well. And then from close 4.4.1.3 in bracket 1 P, we have delta C deviation of 10 mm. So to satisfy both bond and exposure requirements, we have C min plus delta C deviation, so it's 20 mm. And then from consideration of fire exposure, we refer to Eurocode 2 Part 1-2 Table 5.8. So the thickness of the slab should be more than 80 mm, and with that we have axis distance of 10 mm for Ly over Lx of less than 1.5. So in our design, our Ly over Lx is 1, so it's less than 1.5. So from the calculation, our C norm should be greater or equals to 6 mm. So the C norm of 20 mm is suitable for bond, for durability, and also for fire resistance. And then for slab thickness, From fire resistance, we have already known that the thickness must be more than 80 mm. And then from table 7.4n, we can assume that the L over D ratio is 40. So this is assumed. Okay, so we have to first assume an L over D ratio so that we can estimate the dimension of the slab. So in this case, we assume L over D equals to 40. So in this case, D is equals to 150 mm. So H is equals to the D plus half of diameter plus the nominal cover. So we have 175 mm. So based on the thickness of 175 mm, we can calculate the slab self-weight. So 175 mm converted to meter is 0.175 multiplied by the unit weight of reinforced concrete, which is 25 kilonewton per cubic meter. We get a force per unit area due to self-weight of 4.38 kilonewton per square meter. So adding the 1.5 kilonewton per square meter of permanent action, we have 5.88 kilonewton per square meter of permanent action. And then the characteristic variable action QK given is 3.5 kilonewton per square meter. So from there we can calculate the design action, and we get 1.35 GK plus 1.5 QK of 13.19 kilonewton per square meter. So for the analysis, we have Ly over x equals to 1, so it's a two-way slab. So if the Ly over x is greater than 2, then it's a one-way slab. So Ly over x equals to 2 or smaller is classified as a two-way slab. So in this case, we have case number 4, which is two adjacent edges discontinuous. And then the bending moment for Lx direction is 0.36 near the midspan and 0.047 at the supporting edge. And then for Ly direction, which is for location number 1 and number 2, so supposedly this is 0.045 and then this is 0.034 for Ly direction. But in this particular example, we take it to be the same in both directions because they are supposed to be the same. It's just a matter of decimal errors. There are two layers of moment steel at position number 2. So one layer is in the Lx direction and then another layer is in the Ly direction. And then for position number 1 and number 4, there is only one layer of moment steel in this direction, and position number 1 we have only one layer of moment steel in that direction. So the effective depth of the outer layer of steel is H minus cover minus half the diameter of bar, so it's 150 mm, and the effective depth for the inner layer is H minus cover minus bar diameter minus half of bar diameter. So what it means here is that if we are having two layers of steel where one layer of steel is the outer layer and another layer is the inner layer, so this is the D effective depth for the inner layer, and then this is the effective depth for the outer layer. So for the main reinforcement, first of all we calculate the minimum and maximum reinforcements. So S min is given by this particular equation here from 9.2.1.1 of Eurocode 2, and FCTM for grade 25 concrete is 2.6 megapascal if you refer to table 3.1 of Eurocode 2. So as mean as calculated is 203 square millimeter per meter width. So this value is greater than 0.0013 BD of 195 square millimeter per meter width, so it's okay. So we take as 203 square millimeter of reinforcement per meter width. And then as maximum is 4% of concrete cross section. So the concrete cross section is width of 1 meter times thickness of 175 mm. So the as maximum is 7,000 square millimeter per meter width. So based on the minimum reinforcement, we can provide H10 at spacing of 300 to get steel area of 262 square millimeter per meter width. So at positions 1 and 4, which are the supporting edges, okay, so we can use the effective depth of the outer layer because there's only one layer of moment steel. So MSX is equals to MSY at both edges. So it's equals to negative 0.047 times N times LX square. So we get a moment of negative 22.3 kilonewton meter per meter width. In design, we ignore the negative value. We only use the magnitude for design. So when we calculate K value, the moment has no negative sign. So we have K equals to 0.040, which is less than K balance of 0.167. So we don't need compression reinforcement, which is generally the case in slab design. So you just calculate the moment arm Z. So moment arm is 0.96D, which is more than 0.95D, which is not allowed. So we use the moment arm Z of 0.95D in the design calculation of AS. So as required is 340 square millimeter per meter width. So we use H10 at spacing of 225 mm to give AS provided of 349 square millimeter per meter width. So we provide H10 at spacing of 225 at location 1 and location 2, and they are provided at the top of the slab section because these are to resist the negative moments or hogging moment across the support. And then at position 2 of the slab, so position 2 we have MSX and MSY. Okay, so in this case we have two layers of steel. One layer is for the LX direction and then another layer is for the LY direction. So we have the effective depth of the inner layer and also the outer layer. So in this case, we use the smaller effective depth value, which is 140 mm as the design value. So in this case, our design becomes more conservative. So in this case, the effective depth of 150 mm will be automatically satisfied. So for the mid-span moment of MSX and MSY, we have 17.1 kilonewton meter per meter width. So we calculate the K value and also the Z value is more than 0.95D, so it's not allowed. So we use Z equals to 0.95D in the calculation of the steel area AS. So AS required is 296 square millimeter per meter width. So we use H10 at spacing of 250 to give AS provided of 314 square millimeter per meter width. So we provide H10 at spacing of 250 at location 2 with two layers and it has to be at the bottom of the slabs, because they are to resist sagging moment or positive moment. So tension is at the lower part of the slab. So the tension reinforcement must be at the lower part of the slab as well. As for shear, we have VSX at location 4 for LX direction, and we have VSX5 for location 5 of LX direction. And then for the LY direction, we have VSY1 for the continuous edge there, and we have VSY at location number 3 for the discontinuous edge over there. So for positions 1 and 4, they are at the continuous edge. So positions 1 and 4, we can use the effective depth of the outer layer because there is only one layer of moment steel. So VSY1 is equals to VSX4, which is beta Vx or beta By for VSY1 and also VSX4, so it's 0.4 times N times Lx, which gives 31.66 kilonewton per meter width of shear force. So VED is equals to 31.66 kilonewton per meter width. And then from section 6.2.2 of Euro Code 2, we have the design resistance equation given. VRDC is equals to this equation here, and it should not be less than this expression. And then K value is given by this equation, and K value cannot be more than 2 in the equation there. So the K value in our calculation is 2.15, so it's more than 2, so it's not okay. So we set K equals to 2 in the design calculation. And then row 1 is the provided steel ratio. So at positions 1 and 4, we have H10 at spacing of 225. So the provided steel is 349 square millimeter per meter width. So the width is 1000 mm, and then the effective depth is 150 mm. So we get 0.0023 for row 1 value. So you substitute this row 1 value into the VRDC equation, and we get 64.5 kilonewton per meter width. So this is less than the value given by this expression there, which is 74.25 kilonewton per meter width. So that gives VRDC equals to 74.25 kilonewton per meter width. So we compare the applied load effects of VED, or the applied shear force, and then applied shear force is less than the shear resistance of VRDC, so it's okay. At positions 3 and 5, there are two layers of top steel, so smaller d is used in this case. So here we assume that the bottom tension bars are to be stopped at the center of the support. So please refer to the detailing letter. So the shear resistance is based on the top steel with minimum steel of H10 at spacing of 300. So in this assumption, we are assuming that the bottom steel here is stopped at the center of the beam support. So this means that this steel here does not provide enough anchorage, beyond the support. So meaning that the bottom steel here does not provide shear resistance. So the shear resistance is provided by the top steel that we provide to resist nominal moment at the supporting beam. So we are using this as here, for the calculation of the shear resistance. And as I mentioned just now, we assume that the moment here is 0. So if moment is 0, then we do not need any steel, isn't it? but due to the integral action of the beam and slab which are cast together, there is some negative nominal moment there. Okay, but we do not need to know how much is the value of the nominal hogging moment at this support. We just need to provide the steel area, okay, which is 50% of the main bar, and then it should not be less than minimum steel. So in this particular example, 50% of the main bar is less than as minimum. So the steel bar that is provided to resist the nominal hogging moment is as minimum. So at the supports we have VSY and VSX. Okay, so VSY is at location 3, VSX is at location 5. So both shear force is equals to beta Vx and beta Vy equals to 0.26, and then multiply by the design action of 13.19 kilonewton per square meter multiplied by Lx is equals to 20.5 kilonewton per meter width. So the applied shear force is 20.58 kilonewton per meter width. So after that, we calculate the design shear resistance based on Euro Code 2 section 6.2.2, and K value is equals to 2 in this case because the calculated value is more than 2. And then row 1 is based on minimum steel of H10 at spacing of 300. So the AS provided is 262 square millimeter per meter width. So VRDC calculated from this expression here is 58.31 kilonewton per meter width, and then from this expression here is 74.25 kilonewton per meter width. So meaning that the VRDC has to be taken as V min, which is 74.25 kilonewton per meter width, and VRDC is greater than VED, so it's okay. And then for deflection, we check at position 2 with the smaller d. So automatically the deflection for the larger d will be satisfied. Okay, so the percentage of required tension reinforcement for MSX and MSY near the midspan is 296 square millimeter per meter width, as we have calculated just now for the steel required at position 2, somewhere near the midspan of the slab. And then the reference reinforcement ratio rho 0 is 0.005, and then the factor for structural system, because the slabs is continuous in this case. So in this case the slab in both the Lx and Ly direction, they are continuous. Okay, and then this is the end span of the slab and is continuous in that direction for Lx. Okay, so we have slab that is spanning in the Lx direction in this way, that is continuous in that direction. So this is the end span of the slab for a continuous slab in this direction. Okay, and then Ly here is also the end span for the continuous slab in that direction. So K equals to 1.3 for the end span of continuous slab. So rho is smaller than rho 0, so we use equation 7.16.a. So L over D as calculated is 58.2, and then the slab is 6 meter span. So multiplication factor for span that is less than 7 meter is 1. And then the multiplication factor for steel area provided is 314 over 296, so it's 1.06. So the allowable span to effective depth ratio is 61.7, and the actual span to depth ratio is 42.9, which is less than the allowable span to depth ratio, so it's okay. And then for cracking, we refer to section 7.3.3, and we can refer to sections 9.3.1 for slab thickness of less than 200 mm. Okay, so the main bar, the maximum spacing is 3 times the thickness of the slab, or 400 mm, whichever is smaller. So 3H is more than 400 mm in this case, so maximum spacing is governed by 400 mm. And then the maximum bar spacing for the main bar is 250 mm. We have one main bar of spacing of 225 mm and another main bar of spacing of 250 mm. Okay, so if 250 mm has satisfied the maximum spacing, then 225 automatically will satisfy the maximum bar spacing. And then for the secondary bar, we have a limit of 3.5H or 450 mm. So 3.5H is more than 450 mm. So 450 mm is the limit. So our bar spacing for the secondary bar is based on S minimum, which is H10 at spacing of 300. So for spacing of 300 mm is less than 450 mm. So it's okay. So this diagram shows the detailing of the reinforcements that we have just designed. For LX direction, we have reinforcement at this position and this position near the midspan. So let's look at the midspan reinforcement. So midspan reinforcement is H10 at spacing of 250, which is bar number 1 here. So the bar should be spanning in the LX direction, and then it stops somewhere near the supporting beam. So this bar number 1 is placed from here to here. Okay, and then in fact, you have many bars running in this direction, but it will be too messy if you draw details like that. So normally we just draw one bar that represents the length of the steel there, okay? And then we indicate that it has to be placed from here to here, okay? And then we draw a dimension line here, and then we draw a dot here, okay? And then draw arrows on both sides. And then specify that is H10 at spacing of 250, and then this 01 is extra to indicate that this is the 01 bar there, okay, for easier identification. Okay, and then we have a B here, indicate that is a bottom bar. And then we look at the bar 02. So bar 02 are the bars that is resisting MSY near the midspan of LY. Okay, so bar 02 is this bar here that is placed from here to here at the bottom, and then we have all the bars running in this direction. So we don't draw all the bars, we just specify that it's placed from here to here. Okay, and then we draw a dimension line to indicate the region where these bars are placed, and then we specify that is H10 at spacing of 250, and it's bar number 2, and it's at the bottom. So this is bar number 2 here, 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 and here. Okay, if you cut across section AA, you see bar number 2 as the dots here. And then next, we look at the bars provided for the negative moment in the LX direction. So it's bar number 3 here. Okay, so bar number 3 has to be placed from here. Okay, so it's starting from the edge of the support with 1800 mm from the edge of the support. So this is calculated based on the simplified detailing methods. Okay, so this is 0.3 L. Okay, so 0.3 times 6000 is 1800 mm. So these bars has to be placed in this direction. So we don't indicate all the bars, we just indicate that it has to be placed from here to here, okay, with a dimension line, okay, and then with a dots here, and then we just specify that it's H10 at spacing of 225, and it should be at the top, and then it's bar 03 in the cross section here. So this is bar 03 in the cross section. And then to resist the hogging moment in the LY direction is this steel bar here. So this steel bar is bar 04 in this cross section BB there. Okay, so it has to be placed from here, it has to be extended there, so I don't indicate it there. Okay, we just draw the reinforcement until the limit here. It's actually continuous over there, okay, but we don't look at that side. So bar number 4 here is the bar provided to resist the negative moment in the LY direction. So this is H10 at spacing of 225 mm, and it has to be the top bars, okay, and this bar number 04 in the cross section here. So this bar has to be arranged in this direction, so meaning that is provided within this region here, from here to there. And then we have bar number 05, which is the distribution steel for bar number 3. Okay, so remember that we have bar number 3 that is in this direction. Okay, and then we need distribution steel for bar number 3. Okay, we have only one layer of moment steel across the support here, but we still need distribution steel for bar number 3. So that is bar number 5 over here. So bar number 5 has to be placed from here to here to tie up bar number 3. So in this case, it is provided from here to the other side where bar number 3 is extended. So it has to be provided until the length of bar number 3. Okay, so it's from here to whatever location over there. So it's the top layer. So if you cut across section BB, if you cut across section AA, you can see that bar number 5 are these bars there. So these bars has the spacing of 300 mm. And then bar number 6 is provided as a secondary steel to bar number 4. For bar number 6 is this bar here, from here to there. Okay, this is the length of bar number 6. And then bar number 6 has to be provided from here to, actually it has to be extended on this side because this bar number 4 is also provided across this section here. So this section we don't indicate the bars over there, so this is extended there. Okay, and this is the top layer, which is bar number 6. Okay, so if you cut across section BB, okay, you see that bar number 6 are the distribution bars for bar number 4, which has a spacing of 300 mm. And then we have bar number 7. Okay, so bar number 7 are the bars provided to resist the nominal moment. As I mentioned just now, we need the bars to resist nominal moment near the end support because we assume moment equals to 0, but actually it's not 0, it has a negative moment there. But we do not need to know what is the value there. We just need to provide 50% of bar 01 as bar 07. But 50% of bar 01 is less than minimum steel, so we provide bar number 07 as minimum steel. So minimum steel has spacing of 300 mm and it's H10 at spacing of 300 mm and is at the top of the slab section. So we have T there. Okay, so this bar number 7 here has to be provided from here to there. And then we have bar number 9, which is provided as the distribution steel for bar number 7. Okay, so bar number 9 is here, which is this bar here. So this is provided as distribution steel for bar number 7 here. Okay, so it has to be provided from here to there. So therefore, we have bar number 9 in section AA here is the distribution steel for bar number 7, which has a spacing of 300 mm as well. Okay, and it's also at the top of the slab. Next, we look at bar number 8. So bar number 8 is this steel here, which is provided to resist the nominal hogging moment at the end support there, which is similar to bar number 7. So bar number 8 is provided within this length here, so we have a lot of bar number 8 there, but we don't draw all of them, we just draw one bar and then we just provide it from here to there. So this is bar number 8, which is H10 at spacing of 300 on the top of the slab. And then bar number 10 are the bars that is the distribution steel for bar number 8. So bar number 10 has to be provided of this length. The length of bar number 10 is this length here, and then it has to be distributed within this region here at spacing of 300 mm and is at the top of the slab. Okay, so those are all the reinforcement that we need to provide in this design example. So that's all for the lecture in this video. Thank you very much for listening.